Drafts number 117. Thank you. My name is Nick. I am a graduate student at the University of Arizona in the Department of Astronomy. For those of you who are new to our show here in Tucson, welcome. This is Space Drafts. This is Tucson's branch of Astronomy on Tap. Astronomy on Tap, if you're not aware, it is a network of events that are out there amongst the communities around the world, sharing astronomy with you, the general public, in bars and pubs all over the place. There's one in LA, there's one in DC I know of, but if you are new to Tucson, welcome. This is our version of it. We will have two 25-ish minute talks for you. Between those, we'll have 20 minutes for you to step outside to get a bit of fresh air. I know it's a little cramped in here tonight, but that'll be your 20 minutes to get a fresh drink, step outside, enjoy the beautiful night, and then we'll come back to the second talk after that. Let's see here. We also, in each of the talks tonight, we will have a little trivia question for one of you out in the audience to win a little piece of our merch. We don't have it quite set up yet because it's been a little, we're kind of tight on space, but we will have merch available over here during intermission and after the show for a little bit. We do only accept cash, so if you don't have your cash with you, please come back for the next Space Drafts and get yourself a little bit of our merch. We also do accept donations if you are so inclined. Those do help us keep this show running. So if you are so inclined to give us any donations, we would greatly appreciate it. All right, with that, I believe we shall begin our first talk. Here to talk about black holes in their infancy, please welcome University of Arizona graduate student and soon to be your PhD this summer. Please welcome Jeniveve Pearson.
Hello, everybody. So my name is Jeniveve. I am a graduate student here at Stewart Observatory at the University of Arizona. And I'm really super excited to be here today to talk to you about fairies. I guess we'll also talk about black holes in this as well. So, wrong way. All right. So, how many of you know who Cicely Mary Barker is? Anybody? Anyone? Okay. I didn't think anyone would know. Cicely Mary Barker is a famous illustrator and poet who operated primarily in the early 20th century and is most famous for her flower fairies work. She basically drew fairies and flowers, and their associated flowers, for thousands of flowers, and then wrote a poem to go with every single one. And when I was a little girl, we had a copy.
Try it again?
We had a copy of this book right here, the deluxe book of Flower Fairies by Cicely Mary Barker, which is a collection of her poems and illustrations that my mom would read to my sister and I over the course of the period where we were trying to learn how to read. And the pages of this book look something like this. So here are two of the illustrations. These illustrations are a full page, and then you would have a poem associated with it. So here I'm showing you a spread with two full illustrations, but there would have been a poem on either side of those. I'm showing you this page in particular because Forget-Me-Not Fairy, which is this lovely lady in blue here, was my favorite fairy growing up. Mostly, I liked the poem. I think this poem is really super cute. But also, this is what I looked like at the time. So you can imagine why I might have liked her. All right, so for Christmas one year, I received Fairyopolis, which is a book which is part of a larger series of interactive children's novels that have all different kinds of things you can open and put things in and all this. This one in particular is based around Cicely Mary Barker's work. And I was already super excited about all of these beautiful fairy illustrations. And so you can imagine I was super excited to get this book, especially since the pages of this book look like this. So there's this beautiful kind of field journal that Cicely is like a fictional field journal as Cicely Mary Barker is experiencing a summer in Sussex during which she encounters for the first time fairies and begins to study them. So this is truly a field journal. And there are all these beautiful notes and things you can take in and out, and her correspondences, direct correspondences with the fairies. And the pages of this book have aspects like this. So she's like noting that the fairies look like they have butterfly wings, and that they have pointed ears, but not all of them have pointed ears, and some of them wear shoes, but not all of them wear shoes, and she's writing like little comments about these things and posing scientific questions. Now, my mother will tell you that I learned how to read cursive because she taught me. I would posit I learned how to read cursive because of this book. I think today, even still today, this is the book I have read the most of all time. Cover to cover, I read this hundreds of times. I was obsessed. I was going to find the fairies, okay? I was a little bit skeptical that fairies existed because I had not seen them. But like any good scientist, I set out to reproduce the results presented in this book. And so that meant that I did a series of experiments that were similar to the ones outlined in the book, which included leaving out little food treats outside for the fairies to come and get. All I got were ants. I would look religiously for any fairy rings that occurred in my surroundings. But when I didn't find them, I would make them myself, just in case that would encourage the fairies to come. So lots of rock circle rings that were made because of me. And I would sit really, really still in the garden for what felt like hours, but was probably just minutes, as I tried to see the fairies and lure them into a false sense of security so that they would come out and let me see them. Now, unfortunately, all of my experiments ended up with null results. I didn't find any fairies. And eventually, my scientific tenacity was no longer enough to keep me going, and I moved on to different scientific pursuits. Namely, I got another one of these books about princesses, and moved on. But this book still remains one of the big pieces, I think, for me, of my scientific journey. And so today, my scientific pursuit of choice is transient astronomy. Transients are astronomical phenomena which occur on human timescales, observable timescales. Think planets, comets, asteroids, but when we really talk about transients as astronomers, usually we're talking about explosions. So that means novae, supernovae, tidal disruption events, gamma ray bursts, basically any explosive phenomenon in the universe. My thesis work in particular is focused on supernovae. That means I've spent the last 6 years really trying to understand the explosive deaths of stars. And so, I'm going to take you on a little bit of a journey of that, a very interesting aspect of that research. So, let's start with a little bit of a primer. We're going to assume all stars are singular for the purposes of this talk. That's not the case, but for the purposes of this talk, all stars are singular. So, small stars, like our suns, will become red giants, they'll puff up, and then they'll puff up even more, like kind of fluff off their outer envelopes, become planetary nebula, and at the center of which will be a white dwarf. That's the end of those stars. For large stars, something different happens. And now in astronomy, we call these massive stars, not large stars. And so we have reached our first trivia question. How big are massive stars? Are they A, greater than 5 solar masses, B, greater than 8 solar masses, C, greater than 10 solar masses, or D, greater than 20 solar masses?
Please raise your hand.
In the back.
D.
D, 20. That is incorrect. Anybody else want to give it a try?
C.
C, 10. Also incorrect. Back. A, 5. Incorrect. B, that is correct. All right, so massive stars are stars greater than 8 times the mass of our sun. These stars will, at the end of their lives, puff up extra big. we call them red supergiants. They'll be like thousands of times their previous radii. And eventually, those red supergiants will collapse under their own weight and produce supernovae. Okay. Exciting, big explosion. That's great. How do we know that red supergiants produce supernovae? Well, we actually have baby pictures of these supernovae. So here we have a supernova in the center, and here on the side, that's the red supergiant that this supernova came from. And we just so happen to be looking at this field of sky before this explosion happened. So just, someone was taking data not related to the supernova at all back in 2015, and then in 2018, the supernova happened. And so we can actually directly link it to that object. And if we look later, after the supernova has faded, oh, that star is gone. So we know for a fact that that was a star that exploded. All right, that's exciting. Okay, now we come to our first real quandary in supernova science. And this is the one that I have spending the last piece of my thesis discussing. All right, so we know that red supergiants are the progenitors of supernovae. So we can use their baby pictures, those pictures of red supergiants, to determine how massive those red supergiants were before they exploded. Basically, how big are these stars? How big are the stars that are exploding? And if all the red supergiants are exploding, we'd expect the supernova, the cumulative distribution of supernova, to follow this dotted line. Now, this plot is not a great plot, and it is very confusing for people who are astronomers. But these red points here are the actual supernovae observations, and they should follow this dotted line, but instead they follow this black line here. And so what that means is that there is a missing number of massive red supergiants. We're not seeing these things explode, these 20 to 30 solar mass red supergiants explode. And we know they exist because we've observed them in our local universe. Okay, so what's happening? This is what we call the red supergiant problem. Basically the lack of high mass red supergiant progenitors for supernovae. Where are they going? What's happening to them? Now, there are a lot of caveats to the red supergiant problem that I will not go into because they're boring and have a lot of scientific relevance, okay? So we're just gonna assume that this is a real problem, and if you wanna know about caveats, ask me later. All right, so let's assume this is real. Possibility number one is that these objects are exploding as some other type of star. So we have our red supergiant. Over the course of its life, something happens to it, winds or binary reactions, that cause it to become a blue supergiant. Basically rip away the outer envelope of the star so that it looks like a hotter star because you're seeing further into the star. You're seeing the hotter material inside. And then that star explodes. So that's a different type of supernova than the other red supergiant ones. And so that might be explaining why we're not seeing red supergiant supernovae from these high mass red supergiants. Now, this is also a boring explanation, and so we will go no further into discussing this. All right. The second possibility is that they implode instead. What do I mean by implosion? Okay, I mean the star directly collapses into a black hole with little to no transient event. So no supernova happens. It might do like a little burp, but mostly no supernova is happening. And so you get most of the mass of the star collapsing into a black hole without throwing off all this material. Now, this has huge implications for the rest of science in astronomy, because these massive stars are responsible for all of the elements that we see commonly, including the ones that are responsible for you being here today. And so if a large portion of these stars, about 20%, are not exploding, then the material in these stars is not ever making it to you. And so that has implications for our cosmological simulation models. How are we getting better with the universe? And so we really need to understand, is this actually happening? Are these actually real? Okay, so this is a very exciting possibility. And with all exciting possibilities, we need to look at the evidence. Firstly, let's go back to our original picture. And I'm going to posit right here an important piece of information. In the center of this supernova for a massive star, there's one of two different types of compact objects. There is a neutron star or a black hole. Now, the question, and this leads us to our second trivia question, is when do they turn over? So what is the theoretical mass at which stars begin to form black holes? Is it A, 10 solar masses, B, 20 solar masses, C, 50 solar masses, or D, 100 solar masses? Oh, I already called on you, so you can't. Everybody else gotta go. Come on, take a guess. Who said that? D? It is not D. 100 solar mass stars will create black holes, but 90 solar mass stars also create black holes. 20, that's correct. 20 solar masses is at the point where we expect the stars less than that will create neutron stars, and the stars greater than that will begin to create black holes. Okay, so now we've posited this piece of information. We're going to go back to the fairies. When we find something super, super exciting, the first thing we must do is figure out, okay, we have this hypothesis. In this case, the hypothesis that fairies exist. And the piece of information that has caused us to perhaps have this hypothesis is that, in the case of fairies, that I have this wonderful book that suggests that they do exist, and it was written by an adult, crucially. Okay? And so therefore, it must be true. Now, not completely true, because again, I have not seen the fairies. But there's a bunch of different evidence that is sometimes posited for the existence of fairies. Fairy rings. They are known to exist in nature. Mushrooms, grass often create rings. There have been observations of flickering lights that have been widely reported. Things are often move around. These are all the kinds of things that caused folklore to initially suggest the existence of fairies. And unexplained music and sounds, particularly when you are alone in the forest. All right. Okay, what about failed supernovae? We know there are red supergiants, high mass red supergiants. We don't see them explode. What are the other pieces of evidence for the existence of black holes from failed supernovae? All right. Firstly, we know that you must transition from a neutron star to a black hole. All right, and at some point there must be a middle point of that transition. And some models don't explode at this expected middle point. All right, so these are theoretical models of explosions. The red is an explosion, the black is a failed explosion. And you notice there's an awful lot of black between these 20 to 30 solar masses. This is just one model. Some models have different areas where they implode, but all models have some point at which they implode. Okay, all right, that's evidence. We also have the possibility that there's a gap in the masses of small black holes. If you look at binary stars, which are two compact objects orbiting each other, you can see that the mass of the black hole are kind of like these strongly peaked thing where we'd expect this kind of be a somewhat similar distribution to the neutron stars, and it's kind of cut off. And so there's no black holes between 2 and roughly 5 to 6 solar masses. That might be what you would expect if the entire star is collapsing, because that would create a larger mass black hole than these, higher mass objects, which only the core is collapsing. Okay, maybe it's a failed supernova. And finally, when we look at LIGO data, there's an increased number of these 10 solar mass black holes in the LIGO observations. So this is a curve of the distribution of LIGO masses. So these are black holes from gravitational wave events. And you can see that there's this peak at 10 solar masses. Now there's a bunch of different explanations for this, but one of them could be that these 20 to 30 solar mass red supergiants are creating roughly 10 solar mass black holes, and it's causing that peak in our distribution of black holes. Okay, so let's assume fairies are real and black holes are real. How do we look for them? Because again, a scientist never says, okay, it must be real then. We have to actually look. We have to do some science here. All right. So, firstly, let's posit how you might search for fairies. Okay. Important quandary here, if we're doing an observational search. We must first qualify what is a fairy. Okay, I'm showing all these beautiful pictures of fairies here, but this is just one artist's interpretation of a fairy. There's a lot of examples of fairies in pop culture that we can draw upon to try and understand the collective sample of fairies. Okay? This is probably the one you thought of when I said fairies, but there's a ton more. I'm of course awesome. Okay, so just yell out here. What are some of the observables that we should look for if we want to observe all of these fairies? Flight? Okay, so not all of these fly. Puck doesn't have wings. This is Oberon and Tiana, also no wings. The gentleman with the thistle hair, also no wings. Silveriness, gentleman with thistle hair, kind of maybe has some silveriness. But Puck, famously, not super silvery. And the wing scrolls glow pink. So, okay, silveriness is probably not what we should look for. Have one more guess? Anything? Magic. There, okay. That is the one thing I cannot argue against, okay? What is a fairy? A fairy is a magical being. I can say that for sure, it's a magical being. But the physical characteristics of a fairy vary wildly, as we have seen. Okay. So we've figured out what we should be looking for, a magical being. And where should we be looking for them? Well, magical beings are obviously in magical places. Like Fairy, Neverland, and gardens in Sussex. Okay? This was the primary issue with my original experiment, is that I was looking in a backyard in downtown Los Angeles and not at a country estate in Sussex. Okay. All right. Now, where should we look for these? Like, how should we look for them? Because now we know where, but we need an actual observational technique to use. So, childhood me, expert in fairies, and a desperate reader of Fairiopolis, would tell you you must lure them with sweets and look out of the corner of your eye, because you will never encounter a fairy first and foremost head on. You will only see it as a glimpse of movement out of the corner of your eye, and then you have to, develop a relationship with them. Okay. What about for failed supernovae? Let's go back to science. Okay, what is a failed supernova? A failed supernova is a massive star that makes a black hole without a supernova. However, physical characteristics may vary. There are tons of models which say this star will make a little explosion, but it'll look like a supernova, but it's like a lower luminosity supernova. Oh no, it'll look like a luminous blue explosion. No, so not like a supernova at all. Oh, actually it's gonna look like a nova. It's gonna be a gamma ray burst. Or it's gonna have no explosion at all, an unnova. And all of these models have posited all different types of things that it looks like, which, if you're an observer, is entirely unhelpful. So, okay. One of the ways that we look for transient objects is difference imaging. So here, what you're seeing is we take an image of the night sky. We call this our template image. Before there's a supernova, we take a template image. And then we continue taking pictures of the night sky, and we subtract our template image and our new pictures. And so if a supernova happens, there'll be a supernova on our new image, and when we subtract them, a supernova will appear. Now, if you're trying to find something that disappears instead of appears, you would do the reverse process. So we'd have a picture with our star in it, in this case, not a supernova, and then we'd continue taking pictures of the night sky until that thing disappears. And then our difference image would have the image of the star, which is no longer there. Okay, so this is how we're going to look for these objects. But you can imagine this might be kind of a difficult task if you need to be able to observe one singular star disappear. There's a lot of structure here. Subtracting things with structure is difficult, and there's a lot of stars. So we might see a lot of things disappear that might not be failed supernovae. Okay, so I'm going to talk to you briefly about the two best candidates for failed supernovae. The first candidate that was posited was discovered actually here at the Large Binocular Telescope up at Mount Graham as part of the search for nothing. And it's this object right here. This is a red supergiant that was observed in 2007. And then when they went back and looked at it in 2015, it was gone. A disappearing star, a real disappearing star. Are failed supernova real? We'll see. So that original star was 23 solar masses, the expected value that we'd want for a failed supernova. And even better, we've been looking at this object with the Large Binocular Telescope for over 15 years, and it hasn't come back. It's gone. Stayed gone. That's really exciting. It might be real. Okay, so one of the ways that we can say, that we have said, okay, you can figure out if it's a black hole or not if you look in the infrared. Because in the infrared, a black hole should not be emitting no matter what light it is. And maybe in the X-ray if it's green, we'll get to that. But a black hole should not be emitting light. The black hole itself is black, no light. So if you see a source, whatever wavelength, then that indicates that it's not a black hole. Okay, so we're going to look with JRST. We're going to point JRST at this beautiful object, and it's there. There's super bright, it's this top thing here, super bright, especially in these redder filters down here. And the source is clearly detected. So is this no longer a failed supernova? Well, it could be a failed supernova. It could be an accreting black hole. So then what you're seeing, this light, would be the light from the accretion disk around the black hole. But it's been 15 years since it disappeared, almost 20 now. And so that's a really slow accretion onto that black hole. Again, there's only 23 solar masses that need to come into this black hole, and some of them are already in the black hole. Okay, it could also be that there was kind of an outburst that formed a dust shell, kind of dust enshrouding the object, which makes it appear to disappear in the optical. But like you can see ghosts if you look in the infrared, you can see stars if you look in the infrared, even when they're covering themselves with dust. All right, so this object, though, is fainter now, this infrared object is fainter than the pre-disappearance object, which is not what we would expect if it was just kind of like a dust amount of stuff. Like the light should still be there, it should just be in the infrared. So that means maybe this is some kind of merger event, but it doesn't look like any of the merger events we know. So we don't know what this is. We need to continue looking at it with JRST. We have multiple programs looking at this continuously with in the infrared, and then we really need deep X-ray observations because an accreting black hole will have X-ray emission. So that's a way that we can maybe distinguish between the two. Okay, so we found this weird thing. It's not a weird. It's a weird thing is an anomaly until you find another one, and we found another one. So this is M31 2014 DS1, which was discovered in the infrared. It's this giant black blob here in the center, and you can see it's not there. It's kind of maybe still there, but it's definitely not there in the optical. Okay, and this giant black thing was an 18 solar mass general. So again, roughly in the value that we would expect for a failed supernova, but this also clearly detected in JRST. That's a super bright infrared source if I've ever seen one. And it looks a lot like that other candidate. So this is like a weird kind of object, and we found two of them. Okay, if you want to know if something is real or not, 2 is not a staple name. You need to find a bunch. So we need to find a lot of these things. So where should we look for failed supernova? Because now we need to find a survey, not just one or two. We need to define our survey. Massive stars are well known to be in star-forming regions, and massive stars must be the progenitors of failed supernovae. So we should look in star-forming regions. And how should we look? Well, we want to find stars that disappear. Okay, seems simple enough. Surely this is easy. Okay, so enter the HST failed supernova project. This is what I have been working on, back and forth for the last 6 issues. This is the final chapter of my thesis, and I'm still not done. To tell you how this is going. The beautiful Hubble Space Telescope is amazing in that it has been up observing for 35 years. And people have been taking pictures of the sky for that long. So we look at a sample of 31 nearby star-forming galaxies with high core collapse supernova rates. These are the exact star-forming regions where we expect to find failed supernovae. And then we make sure that there are at least 2 epochs of imaging existing already. So previous scientists, they were looking at these galaxies in red filters, because those filters are sensitive to red supergiants. And then we took some template images so that we can try and figure out if things disappear. And some of these galaxies even have infrared observations. So we can actually immediately say, is this in the infrared? And we can leverage that beautiful 30+ long baseline of HST to really look at the entire amount of time. So if a red supergiant has disappeared within those 30 years, we might be able to detect it. So this survey is supposed to find about 5 new failed supernova candidates. Now, 5 doesn't seem like a lot, but when the sample size is 2, that is very large. Okay, so this is the part of the talk where I'm supposed to tell you all the amazing failed supernova that I found. But alas, I'm looking for hay in a haystack. Lots of stars disappear. Turns out, when you look at bright things are variable. They like to do weird, crazy things. And similar, so this is a difficult observational problem. How do we find the weird, crazy stars, and how do we separate them from the real failed supernovae? This is a similar problem to looking at a field. Okay, I didn't grow up with fireflies. I've never encountered this before. But this is a field of fireflies. Where is it? If you were just observing from there, can you definitively tell me that all of these are fireflies? Or are some of them fairies? Are all of them fairies? Maybe all of them are fireflies. Maybe half of them are fairies and half of them are fireflies. But you can't walk up to this field and check. So how do we distinguish between fairies and fireflies? Seems like a difficult observational problem. We need to narrow down a candidate somehow. We somehow need to separate the fairies from the fireflies. But then we might be missing potential objects. What if there's a weird fairy that looks like a bug? What if there's a weird bug that looks like a fairy? And so we have an additional problem in that we already have 2 ideas of what a failed supernova might look like. But we're not totally sure that these are failed supernova. If they are failed supernova, then one of our major diagnostics, J2ST observations, we cannot use to distinguish the fairies from the fireflies. Well, that's difficult. I can tell you that in my sample, every single disappearing object that has J2ST data is in the J2ST data. Does that mean it's a fairy or a firefly? I cannot tell you. And that is a problem when we're trying to understand how many failed supernovae actually happen, and if they actually happen at all. And so, really, the search for failed supernova boils down to distinguishing the fairies from the fireflies. And that is a difficult problem. And so this leads us to my final question, right? I get asked this a lot. Do I believe in failed supernova? Do I believe in fairies? Okay? And the answer to that question is, childhood me could not tell you definitively that fairies did not exist, because there was no observational evidence that they did not exist. However, if I had seen a fairy with my own 2 eyes, I would have been overjoyed. And I will still, to this day, be overjoyed if somebody gives me definitive proof of the existence of a fairy. But as of right now, I cannot say with any confidence that they exist. Thank you. Because I'm a talker, you guys get only one question. Anyone?
When you show the different models with the likelihood of failed supernova, why do some have them more likely to happen at higher masses?
Yes. It's a good question. And I'm an observer. And so the exact, I will repeat the question, hold it. We gotta go all the way back there. All right, so the question was, in these models, why do some of them have more failed supernova at higher masses than others? And why are the black regions different for the different models? I'm an observer, which means I cannot tell you exactly what happens in the theoretical model. I can tell you that there are a lot of knobs that get turned that cause different things to happen, and that this is only one set of models presented in one paper, and sometimes these black regions are over here. All right, this is endlessly frustrating to me, as you might imagine, as somebody who's trying to find failed supernova. I don't even know if I'm supposed to be looking for 10 solar mass things versus 20 solar mass things, but we'd expect 20, that seems reasonable. Yeah, there's like slightly different conditions in these models that's causing them to explode or not explode at different times. I should say, supernova models don't explode. They're doing a little bit of magic to make them explode, and so if you see a supernova model that doesn't explode, that's like expected. So it's maybe not as an exciting piece of evidence as I wanted to be.
One more round of applause for Jeniveve. All right, so with that, we will take we'll take a little bit more than 20 minutes. Go grab another drink from the bar, take a little breath outside. I'm sorry, it's a little cramped in here today. Once again, don't forget to tip your bartender. We will be back here at 8:30. See you all then. our second talk of the evening. We're going to be hearing a lot about Saturn's rings from our wonderful speaker here, LPL postdoc, Dr. Zarah Brown.
Thank you so much for coming. I'm so excited to have you here. This is a talk about the age of Saturn's rings. And I've named it Ancient Icon or Cosmic Nepo Baby because secretly the other aim of this talk is to, for me, a millennial who went back to school at 29 with 18-year-olds, to convince you that somehow I am still also myself young. Yeah, here's a picture of me going back to undergrad. Okay, so I, as Nick said, I'm a postdoc at the Lunar and Planetary Laboratory where I got my PhD in 2023. And I also put in the scale model of the solar system on campus. So if you see that, that's me. You should go to it. Thank you. And as an undergraduate, I studied Saturn's rings at the University of Colorado Boulder. And here's a picture of me with a 1/3 scale model of the Cassini Space Telescope, which we'll feature later in this talk. And where I am actually young before this and before this, which is here. So let's get into it. Saturn's rings are the brightest, largest, and most resplendent in the solar system. There's the A, B, and C ring. They've got all of this structure, like a very 70s looking line pattern rising from the resonance frequencies with various moons. Are they old? They're gorgeous. We'll just say that. Okay. So Galileo was the first to observe the rings in 1610 with his fancy new telescope. So when he observed them, he drew them like this. He was a little bit confused, confounded. He said they looked like lobes or ears or maybe love handles. Rude. Okay. But then in 1612, they disappeared, which was very confusing to him. He was confounded, and even more confusing, thank you, friends and family, in 1613 they reappeared. So what was going on with this? Well, the thing is that Saturn's rings are extremely flat. They are approximately 10 to 30 meters thick in most places. And so for all of you heathens on the imperial system, that's about 32 to 98 feet thick. And so they're about 270 kilometers from side to side, which is extremely thin. If they were a sheet of paper, if you took a standard size sheet of paper and scaled it up to the size of Saturn's rings, it would be 10,000 times too thick. So they're extremely thin. So what happened is they just disappeared in an edge-on view from the Earth. So yes, in 1850, some dude who I can't remember, we don't really need to center white male individual scientists in the story of science, especially because I can't remember this guy's name, James Clerk Maxwell, whatever. He determined that they could not potentially in any shape or form be a solid, continuous disk, that they must absolutely be made of individual particles, and indeed they are. They are made out of individual particles as small as particles of smoke and as large as apartment buildings, even larger. Most of the particles are the size of large boulders, the size of small boulders. Thank you. And if you don't get that reference, you were probably not chronically online in January of 2020. Okay, so each of these particles is made up almost entirely of water ice, with a small component of other dark rocky material that we will return to later in this talk. But real quick, I'm going to take a detour, which I had like 5 different slides, and I cut them for length. But if you can see here, you probably can't. It says W. Hartman, who is a local scientist, alumni of the Lunar and Planetary Laboratory, and an amazing artist who did this image. And I'll just plug his show. He's got a show at the Planetary Science Institute here in town, May 30th. You should totally go see it. He's incredible. This is me meeting him in 2018 and totally fangirling out. We both showed, and he continuously shows at the Art of Planetary Science, which is an art show hosted by the Lunar and Planetary Laboratory, which I led for a year. We've got current leader Sierra Foot in the back, and our other speaker, Jeniveve, is also a co-leader of this event. It's incredible. It'll be held next February. We'll be celebrating 50 golden years of Voyager, and it's cut off, but the submission is going to be open in the fall from August to December. So if you are an artist or if you dabble, I highly encourage you to submit. Okay, so let's move on now to the big question. Are they old or are they young? So just based on whatever information you're coming to this event from, who thinks that they're ancient icons and they may be old? Just raise your hand. Okay, we have a few bold people willing to participate. Okay, how about Cosmic Nepo Baby? Who thinks that they're young? Yes, okay. All right, lock in your answers and we'll have it revealed by the end of the talk. All right, if these rings are old, for most of the 20th century, scientists assumed that they formed with the planet about 4.5 billion years ago as the solar system formed. Mommy is doing it. It could have formed from gravitational instability or from a disruption of a moon early in the solar system, maybe in the late a heavy bombardment when a lot of things in the solar system were getting kind of fucked up, to be honest. Okay. For this, the rings would need to be more massive to persist this whole time. Everyone has a big butt. Let's talk about yours. Okay, this is a Pee Wee Herman reference. Dating myself further. Okay, but why are they bright though? So we'll talk about why this is a problem in the next few slides. Okay, so but they could be young. That could happen from an impactor or tidal disruption of an icy moon somewhat more recently in the planet's history. And the rings could be less massive for that. But, again, the timing is very convenient and honestly a little sus. Okay, so let's talk about problems with the young ring theory. Okay, so the solar system formed from a cloud of collapsing cold dust that formed a disk, and eventually planets coalesced out of it. And that's even before you get to the primordial solar system. You've got the late heavy bombardment there. Life arises on this planet 3.75 billion years ago, which is honestly very early. Go life. The great oxidation event where plants proliferated and changed the gaseous atmosphere of this planet 2.4 billion years ago. Animal life arose 600 million years ago. And then you've got dinosaurs finally 230 million years ago. They did die, sorry. 66 million years ago, and then finally Homo sapiens 300,000 years ago. So dynamicists who model what has happened with Saturn's rings think that if they did form early or relatively recently, that would probably have been 100 million years ago. So that is like right in time for us. And what are the odds that we are so special that it would be just like perfectly timed like that? I don't know. Maybe we're extremely lucky. And if I haven't told you exactly how old I am now, this pixelated image of Britney Spears album cover tells you exactly how old I am. I'm that old. Okay, so let's talk about some problems with the old ring theory. Okay, so the thing is that dark material that's falling on Saturn's rings falls everywhere in the solar system. And it's micrometeorites. These are scientists in Antarctica looking for micrometeoritic material in the snowy expanse down there. It's a great place to look for them because there's not a lot of other stuff going on, not a lot of other dirt material to distinguish it from, and it's dark material against a white background. This is scanning electron micro images of what this micrometeoric material looks like. This is something that I actually knew about before I became a scientist because between undergraduate degrees, I worked for a science toy company. And we sold this neodymium magnet, which is a very powerful magnet, and we told people you can go up in your roof, on your gutters, and actually look for micrometeorites because these objects are, some of them made mostly of iron. They can be magnetized, and they fall on your roof, and they fall into the gutter, and you can collect them. Turns out, like, some people were kind of like low-key falling off their roofs, so we kind of stopped telling people about that. So I'm not telling you to do that, but I'm just saying, if you had a neodymium magnet and you were already up there and I was reliable, you could look for them. So we sold this magnet for $16, not a bad return on investment for a magnet. We also sold this geyser tube, which would hold almost an entire stack of Mentos on top of your 2-liter cola, and then there was a 2-foot string and a pin, and you could pull it so that it would all go at one time. And then, like, slightly less exciting, clear safety glasses, but like, it's a good deal, right? Okay. All right. So the next job I had was with Dr. Larry Esposito at the University of Colorado. He discovered Saturn's F ring. Go Larry. And he really was an early champion of this idea that the rings could be old and that they could stay pristine even with all of this micrometeorites falling on it constantly for millions of years because there's so much activity in the rings, things are colliding and recoalescing. Maybe that dark material gets recycled into the interior. So this is a potential savior of the old ring theory. So one of the ways we know, and the idea is like early results from the Cassini spacecraft placed constraints on the ring mass, and they were heavier than they thought prior to it. So how did they know how heavy the rings were? Well, it's from this type of observation called a stellar occultation. And to do that, Cassini arrived at the Saturn system in 2004 until 2017, and it performed dozens of these observations, hundreds of these observations, where it looked through the rings at a bright background star, and as it passed over, it would record the amount of light from the rings. And you can see here that the rings are blocking some of this light. The more material is there, the more light is blocked. So if you do that many times and stitch them all together, you can see how thick the rings are as a function of distance from Saturn's center, which is what you're seeing in the top plot here. So you've got the A ring, which is sort of a medium thick, the C ring, which is relatively thin. All these little spiky things are resonances with moons. And of course, in the middle is the B ring, which is very thick. So you can see it's very thick, and also it's kind of noisy at the top, and partly that's structure from resonances, but also it is just noisy data, and that's because very, very, very little light is leaking through in this B ring region. And the problem with that is that a brick wall will block out 100% of the light from a background star, but so will 10 brick walls. So it's a little bit hard to measure how much mass is in this B ring because it is so thick. So what are we gonna do? For most of the mission, Cassini orbited outside Saturn's rings as it was observing Saturn's atmosphere, various moons, and the rings. And that's because this region between the rings and Saturn is a sort of a dangerous place to be because material from the rings is infalling into the top of the atmosphere all the time, and the amount of material, the frequency of this, and the size of these pieces that might be falling in was previously unknown. So that's sort of like the danger zone. But after 13 years of orbiting and collecting data, and honestly like kicking a ton of ass, they went ahead and in the 2.5 months before the final plunge into the top of the atmosphere, they went ahead and threaded the rings. Isn't that so cool? They did 22 orbits, threading the rings, and what that allowed them to do was, by measuring the velocity of the spacecraft down to the fraction of a millimeter, it was able to basically determine the difference in the gravity from Saturn itself and from the rings, and effectively weigh the rings. So that tells us the mass of the rings, and it distinguished between the old rings and the new rings hypotheses. So, before we do that trivia, cliffhanger. Okay. So the question is, Ghostbusters. What birth year defines when a person should rightfully be considered old? Is it A, 1610? Is it B, 1997? Just yesterday. C, if you have ever owned and operated a cassette tape. D, if you were able to finance a home entirely on your own salary. Or E, any year in the 1900s. You Gen Z are so mean. Okay, just kidding. That's a mean trivia question. That's not really the real trivia question. You can answer it for yourself in your heart. Okay. All right, the real trivia question is, how wide are Saturn's rings? Do you remember? Is it A, 170,000 kilometers? Is it B, 270,000 miles? Is it C, the length of a standard sheet of paper? D, is it 2.7 times 10 to the 5 centimeters? Or E, 2.7 light years? Okay, raise your hand. Oh, I saw you first.
D.
It is D! It is D! It is 2.7 times 10 to the 5 centimeters, which is conveniently the same as 270,000 kilometers. And because it's the metric system, it converts easily. Okay. There's my plug for the metric system. Okay. All right. So now, we're going to tell you whether the rings of Saturn are old or are they young. Are you ready? Drum roll, please. All right, in 2019, Yes et al. Measured the implications of Saturn's gravity field and ring mass, and they found the rings to have a mass of approximately 1.54 times 10 to the 19 kilograms, which is about 40% of the mass of Saturn's icy moon Mimas, not the Death Star, which is light enough to absolutely disqualify the old rings. So, she's a cosmic memo, baby. Kudos to everyone who guessed that at the beginning. And Baby Ghostbusters. Okay. So I guess God said he liked it and he put a ring on it, okay? All right. So here's your epilogue. This happened, dynamicists have determined that this would have happened no earlier than 100 million years ago. So you can imagine that was in the Cretaceous period, dinosaurs roaming the earth. And you can just imagine like a dinosaur looking up and seeing this totally catastrophic breakup of an icy moon in Saturn's system, as I did here with this original painting, which is bought and sold. Until actually I was putting this talk together and I realized like, oh yeah, it's not visible to the naked eye, and I looked it up and they're like, yeah, probably dinosaurs, there's no way they could have seen it. It might have been slightly brighter than it was before. So I guess if a dinosaur was like really paying attention, they might have noticed it. But you know, there's a difference between like art and peer review, okay? And those things are both important. Okay. What am I talking about next? Oh, Baby Ghostbusters. Okay. So the thing is that Saturn's rings are actually disintegrating. So people who do dynamical evolution can tell you that not only are the rings falling into the top of the atmosphere from the middle, pieces are getting lost out from the edge as well. And furthermore, they're getting lost, baby Ghostbusters. They're getting lost from the middle too. So those pieces of ice that are out there floating in space get impacted. Good job, Sam. Okay. They're getting hit by light and impacted by micrometeorites, and some of that icy material is getting liberated and sublimated into the surrounding region, so much so that the rings have their own atmosphere. And if any of that material gets magnetized or ionized, then that material will actually flow along magnetic field lines into the top of the atmosphere so much that it's changing the chemistry of the upper atmosphere of Saturn and in a way that is connected to these rings. So dynamicists have said that there's no way that the rings are going to last for more than about 100 million more years. So that means 100 million years on one side, 100 million years on the other side. We're here at like the exact perfect moment to see these rings. And in that way, you can all consider yourselves extremely special to be here for this moment. Then again, maybe rings are not actually so rare. So if we look at the other giants in the solar system, in the outer solar system, we can see Jupiter here from JWST data. We've got Uranus and Neptune here. In ALMA and JWST respectively, and they all have these faint tentative ring systems. So maybe all of these planets had their turn to have this resplendent, amazing ring system, and maybe it's just Saturn's turn now, and maybe it's not that particularly special. But I didn't want to leave you on that note, so leave you here. This is the backside of Saturn, where she's occulting the sun, taken from Cassini. And if you were alive in July 2013, wait, what's a decade amongst friends? 2013, then you were actually in this picture too, because right here is the Earth. Carolyn Porco, who was organizing images for the Cassini spacecraft at that time, organized something so people could come outside and wave at the moment this picture was taken so that they can be in the picture. So in the end, you know, we're all here in this large expanse of space and time for a fleeting moment. It doesn't even really matter if you're old or young. No, you should just live your life and enjoy the fact that we are lucky and we do live at a very special time in the solar system. So thank you very much for your attention. I'll take questions.
Your questions? I have a question.
Yes.
So Cassini's grand finale, did they ever go into any of the gaps in the rings?
During the grand finale, did Cassini ever go into any of the gaps in the rings? The answer is no. That would have been much harder and much more dangerous and much more likely to explode the spacecraft into a million pieces. So they didn't. No, they didn't do that. Yes?
Have they done any analysis on the other planets to see how old their rings are?
Have they done analysis on the other planets to see how old their rings are? The answer is no. And there's probably just like scant information on that count. I think the information on Saturn's rings hinges on a few things that are a part of why Saturn is so special. So the cosmic dust analyzer on Cassini did take measurements of the rate of micrometeoritic impact while it was threading those rings, and that's part of how they arrived at the 100 million years left number. And they also were able to do this gravity analysis, part of it based on resonance locations in the ring to do some gravity measurements on the interior of the planet, and that's not possible with these other tenuous rings. So it's pretty special that we have this system to test things out on. Yeah. Mike?
To follow on that question, would you prefer to spend resources on going to the moon or going to look at the other planets in their rings?
Would I prefer to go to Earth's moon?
Yeah.
Or to the
what
other-
we've been doing versus going to look at the rings on the other planets?
Go look at the rings on the other
Answer
planets.
his question.
That is a great question. My partner's been watching For All Mankind, where they spend a lot of time on the moon, and I have some opinions about the ethical nature of colonizing the moon. But it's like so hard to say. They're already doing cool missions upcoming to the Jupiter and Saturn systems that I am very excited about, including the JUICE mission and Europa Clipper. So I'm just gonna vote for what we already, all as a nation, already voted for with our tax dollars, and say, let's go back to Saturn and Jupiter. Yes, baby.
The same way that Saturn has an impact on the rings as pulling the material into the planet, do the rings have an impact opposite-wise? Are they pulling outward from the planet itself?
That's a great question. See, I picked him because he's smart. So I mentioned that Saturn's interior gravity has an impact on the rings. So actually, this paper, I didn't say anything about it, but in this observation, they found out some very interesting things about the interior gravity of Saturn from these observations, including the fact that there's differential rotation. So the deeper you go in, there's a different rate of rotation of the whole planet, which was important and very cool. So his question was just how you can tell things about the interior of Saturn from looking at the rings. Can you tell things about the rings from looking at Saturn? And the answer is you could if you had a amazingly, incredibly, stupidly, improbably sensitive instrument, because the rings are a lot less massive than the entire planet of Saturn.
So not like the moon creating wave or tidal phenomena here. Is there some what is the mass of the rings compared to the moon?
So to our moon, I think, I was just looking at it, so the mass of the rings is 40% of Mimas, and I think it's like 1/2000th the mass of our moons, so they're relatively not that massive. And so it just as your individual mass has an impact on the motion of the Earth, it's just very small because you are very small. Because you're so skinny. So yes, too hard to measure. Okay, one last question? Right here, Allison.
Okay, for the atmosphere, transient atmosphere that shows up, is that long-lived, or is that an exosphere or ringosphere?
Yeah, so Allison's asking about the ring atmosphere, and is it transient? Is it long-lived? It continues to be replenished, just like an exosphere is. So like the moon has a small amount of material that is in a gaseous phase around that planet because of the sun shining on it and micrometeorites and such. So the atmosphere of Saturn's rings, I believe, is the same. It's continuously replenished in an exosphere-like way. Yeah, thank you.
One more round of applause for Sarah. Oh boy, let's not drop that. All right, with that, that will bring Space Drafts number 117 to a close. We will not be having Space Drafts next month. Our next show will be in July. Let me get the date up really fast here. I believe it is July 15th. Yes, July 15th will be our next show. Same time, same place here. Thank you all very much once again for coming. Don't forget to close your tabs and tip your bartenders. And we will see you all back here in July. Have a good night.